Hello everybody, this is Gabe Palmer back at you in operating systems, and we're going to be talking about our second segment on synchronization, which is atomic instructions. At this point, you've learned what critical sections are, you've learned why we want them, and we've talked about multiple software implementations and done exercises in thinking about those software implementations. Now we're going to move on to hardware support for synchronization. So we saw in the software implementation of critical sections that we wanted to protect shared memory data structures. This could be in multi-threaded processes, this could be in the kernel, this could even be in shared memory between two separate processes, even if they're single-threaded each. And the challenge here was effectively that we were using shared data structures to protect those shared data structures. We had a lot of logic that went into essentially trying to synchronize different pieces of the critical section machinery together around large shared data structures. This often involved a lot of spinning where we were waiting for access to various parts of the critical section or of the critical section apparatus, and required O of n in the bakery algorithm, where n is the number of threads in the system, amounts of storage and time consumption. So this is not something that we can actually do practically. That's far too expensive in both memory and CPU. And really it boiled down to the fact that with the bakery algorithm, we had these massive arrays and we had O of n costs. And when we kind of back ourselves into a corner like this with software logic, then we often just need to ask the hardware to effectively come save us. And in this case, that's what, in the history of computer science, we've done. We've essentially said, hey, hardware, is there anything that you can provide for us? Computer engineers, give us something good. So on the one hand, they've allowed us to disable interrupts, and there are specific instructions within the ISA for disabling and enabling interrupts. You can see these being used and implemented in, or used, you can see these being used in spinlock.c and xv6. And that's simple. It just disables preemption on that specific core. So this is one way that we can actually work towards critical sections. But the other way is atomic instructions. And these are effectively instructions within an ISA that do multiple things that are all atomic, which is to say they can't be preempted in any way by interrupts on this core or by operations, including atomic instructions on other cores. We're going to dive into both of these. So the first one is disabling and enabling interrupts. These are specific instructions within the ISA on x86. These are CLI and STI, CLI and STI. CLI says to disable interrupts, and STI says to re-enable interrupts. These are privileged instructions, which of course means that only the kernel can execute them. Think about why that is. It's really, really important that they are privileged instructions. Think about why that is. Relatively straightforward. If user level could disable interrupts, then user level could disable interrupts and then go into an infinite loop, and the kernel would never have any recourse to ever switch away from that process. Timer interrupts are there to ensure some amount of fair access to the CPU. When one process goes into an infinite loop, we can switch away from it. If a process could disable timer interrupts, then you no longer have that escape hatch. So CLI and STI just clear and set the interrupt flag. What that means is that there is usually a status register on every architecture, every processor. In x86, it's called the eFlags register, and that includes a number of bits for things like whether a condition ended up being true, whether a greater than check was true, etc., that type of stuff. But it also includes a special bit that essentially tells us whether interrupts are enabled or disabled. And client STI are simply instructions to be able to set that bit to either 1 or clear, right? And when the CPU is executing along, if the bit is set, then if the bit is cleared, then the processor will not check for interrupts each cycle. However, if the bit is set to 1, then the processor will be checking to see if an interrupt has been fired every single cycle and will cause it to happen. So essentially, executing CLI disables interrupts and STI re-enables them. When you enable STI, that's exactly when some of the interrupts will fire that happened between when you did CLI and STI. If we look at what a critical section might look like, you're going to see this diagram a lot. We have lock and unlock. We'll see that there is a abstraction called a lock or a mutex. And that is used throughout the literature and throughout implementations to denote critical sections. So the code between lock and unlock is effectively critical section, as you see here. And then, of course, there's some normal processing, which is a proxy for normal processing within an application. And then we go back and take the critical section again. And if we want to implement critical sections using CLI and STI, then all that we do is implement lock and unlock by executing CLI and STI, which is very, very simple. The problem is CLI and STI only set the interrupt bit in the eFlex register on a specific core. So they disable interrupts on this core, but not on every core. So they can only be used to provide a critical section within this specific core and no other. So they're not a general solution for critical sections. They do not address parallelism, only concurrency. So their limitations is they only work on a single core and only within the kernel because, of course, they're privileged instructions. So the other way that hardware helps us out is effectively by providing atomic instructions. So these are extensions to the ISA, new instructions that we can execute that again do multiple operations in one atomic go. It can't be preempted, and if it's doing operations on memory, then those operations cannot be preempted between cores. So atomic instructions are usually some combination of a load and store with some types of logic. That might be some manipulation of data, might be some operations like adding, subtraction, etc. It might be some conditional logic, but they all essentially have a load, a store, and some other logic all put together into a single instruction. All of that load, the logic, and the store execute atomically. So can't be preempted. It all executes at once or none of it executes. So what does that look like? One of the simplest atomic instructions is fetch and add, or FAA, which you essentially see pseudocode for here. I'm going to be showing you a lot of C code within this lecture, and that C code, you have to realize that I'm showing you C code simply because it's kind of a way that we both understand logic, but it's not implemented really this way, right? FAA is a single instruction, so it does not have any C code that corresponds to it. It is a new instruction. You have to actually execute it as assembly. So I'm showing you the C as a kind of proxy for the overall logic. So what is fetch and add here? We pass in a memory address that we're going to do the loading and the storing, and some integer value that we're going to add to that memory value. So we load the memory value from memory, which is dereferencing the pointer. Here we're going to store it in something, just a local variable called a nit, and then we're going to write out right back to that memory the initial value plus the value that you're trying to add to it. And you can see that the final thing is that we return that initial value. So we load a value, we store that value plus something added into it right back to memory, and we return that initial value. This is what fetch and add is. And I just want to implore you to remember that this is all atomic. This is all a single instruction. All of that load, store, and add, all of that is done atomically. We don't have interleavings between any of these lines of C code. They are all a single line, right? No other core can see intermediate values. Two cores trying to do fetch and add at the same time. You can really think of them as being sequential, one after the other, etc. So this is fetch and add. It's one of the simplest atomic instructions, but we can already see that it's actually pretty useful. We started out by talking about a single problem, by motivating synchronization with a single problem. And that was a counter. How do we actually implement a counter that does plus plus and minus minus, right? So here you actually see an example of implementing a counter using fetch and add, where we have two functions, counter inc to increment it by 1 and counter dec to decrement it by 1. And you can see that both of these are simply implemented by just doing fetch and add of 1 and -1. So we don't care about the return value. All that we care is that the load, addition, and store are done atomically here. So we don't have interleavings at all. So that's really, really powerful. But there's another abstraction that's pervasively used in systems and in some programming language environments called reference counts. And it's a little bit more complicated, but I want to go into it as an example. So reference counts are really important because they're kind of a manual way to perform garbage collection. What that means is you can imagine kind of the number of pointers coming in and pointing at some node. You can think of these like arrows pointing into some node. Each of those is essentially a reference from some node to another. And what we can do is we can keep a count in every single node of how many other nodes reference it. And we know that when all of those arrows are removed, that nobody references the node anymore and we can free it. So the Linux kernel uses this, x86 uses this, most systems use this. This is a very common form of kind of manual garbage collection in C code bases. So how do we implement that? Well, to take a reference for a node, to add essentially a link, we simply do fetch and add and 1. We want to increment the link by 1. We are taking a reference to the node. However, when we release a reference, it's a little bit more complicated because when we release a reference, the caller of ref release is going to check the return value to see whether it should actually free the memory as well. So we do fetch and add, decrementing by -1, but then we check to see if the return value before we did the subtraction was 1. If the value in the counter before we did the subtraction was 1, that means we are the last reference that is being removed to that node, therefore we should free the memory. So this is a pervasively used structure, and it uses fetch and add to be able to implement it. Reference counts are used pretty much everywhere. Let's go to a little bit more complexity. Test and set is a slightly more complicated instruction that has kind of C logic that corresponds to something like this. So test and set takes in only a memory location now, and it will read out that memory location, do a load from that memory location, and essentially return that value that it loads. So it will return what the memory location was before we do anything with it. And what test and set does is it just sets that memory location to true. So it will set a memory location to true and return the value of that memory location before it was set to true. And again, this is all done atomically, right? So if, again, we wanted to implement a critical section abstraction like this, where now we need to implement lock and unlock, then we can do that relatively simply using test and set. I've included the logic for test and set in the upper left so that you can remind yourself, and you can see the implementation for lock and unlock. For lock, all that we're doing is essentially spinning on the value of test and set. So while test and set returns true, which is to say that the value in the lock variable is true, we keep spinning. However, when that lock value gets set to false, which means that there's nobody in the critical section, then the first test and set thread, the first thread executing test and set that executes test and set will both return false, because that's what the value is, and atomically set that lock variable to true, so that any other thread that's spinning trying to access that variable will see it at that point as true. So only one thread will be able to go into the critical section and will execute there, and then we'll finally set lock equal to false. Again, when lock, that variable, gets set equal to false, we know what happens. The next thread that's spinning, waiting for it to be set to false, will see it as false and set it to true. Test and set will proceed, right? So going through the logic here, just to make sure everybody gets it. When the lock is false, then test and set will both set it to true and return that it was previously set to false. That will trip out of the while and go into the critical section, while also preventing other threads from being able to go into the critical section because lock is set to true. Otherwise, we'll see the lock being true, in which case test and set sets a lock equal to true. Well, it already was, so that's okay, doesn't really matter. And returns true, because that's what it was previously. So you can see when the lock is already true, test and set actually doesn't do that much, right? And that's by design. We want it to keep spinning, right? Now, of course, the lock variable must initially be set to false. And I'd like you to think for just a second, what are the problems with solution in terms of the three criteria that we've been talking about for a critical section? Mutual exclusion, progress, and bounded wait. Pause, think for a second, and come back. Okay, for mutual exclusion, I just went through all of the logic for why mutual exclusion is provided by this solution. For progress, if nobody is in the critical section, then either nobody has been in already and the lock is initially set to false, or a previous thread had exited the critical section, setting the lock equal to false. So in both of those cases, if there's a thread within the while loop executing test and set, the first time it executes test and set, it will return false, therefore trip out of the while into the critical section. So progress, when nobody's in the critical section, we are guaranteed to be able to go in within about an amount of time. Bounded wait, however, now imagine that we have n threads all spinning in the while loop that we see here. The problem here with bounded wait is that which one of those threads is actually going to have the test and set actually resolve to false and therefore be able to go into the critical section. It's actually up to the hardware, effectively, which one of the test and sets in a parallel system, for instance, will be able to succeed. The hardware does not have any logic in the test and set atomic instruction that somehow ensures bounded fairness. So bounded fairness is not provided by a test and set based critical section. Now, there are critical sections that are implemented with test and set, and systems that usually simply are making the trade-off that bounded wait is not as important as having a simple and pretty fast implementation of critical sections. If you have a critical section that's not often going to have many different threads trying to contest it and get into it, then this is a fine trade-off to make, right? Okay, now let's go to the big daddy atomic instruction, compare and swap. I'm going to show you the thread for compare and swap, but my experience with students looking at it is that it is really hard to kind of understand the core of what it's doing. However, I'm convinced that the core of what it's doing is relatively simple, but you just have to have the English for it. Once you understand the English, then we'll go on to the code. So I'm going to read it. So you pass in a piece of memory, a word in memory, into compare and swap, just like you did with test and set, right? You pass the address of the memory in as an argument. If that memory holds what we think it holds. What we think it holds. Okay, so we also pass into compare and swap the value that we think that memory holds. Okay, so we pass at least two values into compare and swap. The memory and what we think that memory holds. Okay, cool. If the memory holds what we think it holds, what we pass in as an argument for its value, then update it to hold another value. So compare and swap then takes three arguments: the pointer to the memory, what we think that memory holds, and what we want that memory to get changed into if it does in fact hold what we think it does. Okay? That's the core of the logic behind compare and swap. And then it simply returns true and false based on whether that update was actually made or not. So it returns true if the update was made, i.e., if the memory holds the value that we thought it did, then it got set to the value we returned true. However, if for some reason the memory does not hold the value that we think it does, then compare and swap will return false. That's all. That's what compare and swap does. But it's an immensely powerful operation because what we have below it is an example of how you might use it. And it's a very common pattern for using compare and swap. In the first instruction, all that we do is read the counter. This is with a normal load. This example is the operation 1 is not part of compare and swap. It's not part of the atomic operation. So we read the counter value, okay? Then we might do some operations. We might formulate some new value that we want the memory location, the counter, to hold, okay? In this case, we might take the counter and add 1 to it, right? Okay, great. So if the counter value holds what we think the counter holds, then set it to that counter plus 1. Okay, so then operation 2, if the counter holds the value that we read, then operation 3, update it to hold that value plus 1. However, what you have to understand is that even if lines 2 and 3, which are effectively compare and swap, both of those two lines are one atomic instruction, you could still have a preemption between line 1 and that compare and swap on 2 and 3. Because we can have a preemption between where we're just doing a normal load and where we're doing the atomic instruction, it's possible that another thread did this entire sequence of logic and changed the compare and swap value so that it's not what we think it was, right? Not what we stored as, not what we loaded from the counter value. So, if we notice that compare and swap returns false in this case, we can just go back up to operation 1, read the counter value again, it's likely different from what we read before, and then try to set it to that value now plus 1, right? So we just try again. And if we look at the code for this, it's going to look something like this. We're going to have some sort of a while loop, and we're going to read out the value from the counter in memory, and then we're going to execute compare and swap, where we essentially say, I want to change the counter to val plus 1 if that counter is set to val. And if compare and swap makes the update successfully, it returns true, then we just break out of a loop. However, if it's not true because someone else was executing this exact code and we were preempted by that something else between lines 2 and 3, then we don't break out and instead we just go and do the while loop again. So this is essentially the logic behind compare and swap. If we look at the actual code or the logic behind compare and swap, it looks something like this. We have our compare and swap code, and it will take the memory, the value that we think is in the memory, and the new value we want the memory to be set to if it is set to value. And it will essentially look something like this. If the memory value is not equal to val, then return false. We are not going to do some sort of an operation. So you can see compare and swap includes a load and some form of a conditional operation, right? If, however, we know that the memory is set to val, now remember, this is logic, but remember, all of this is conceptually atomic within the compare and swap instruction, right? Okay, so if we know that the memory is val, then we're going to set it to the new value and return true, right? So this is effectively what compare and swap is, and we see below how we might implement our lock code, our critical section using compare and swap. So again, we have a while loop, and we're spinning while we do not successfully make the modification to the memory, and we essentially just say, well, I want to update the lock value in memory. If it's set to false, then I want to change it to true. While it wasn't false and we did not successfully change it to true, then keep spinning, right? If the lock value was false and it was successfully atomically set to true, then it will return false and will break out of the while, right? So we go to the critical section, and when we're done with the critical section, we want to unlock, then we just set the lock equal to false, which allows the next thread to execute a cast successfully, set the value to true, and take the lock, right? Go into the critical section, right? So let's think through the logic here, just make sure it all makes sense. If the lock is false, then we're going to notice that the lock is false and update it to true and return true. The compare and swap had the successful clause where it did make the modifications because it accurately predicted what was in memory. However, if the lock is already true, then when we say, I predict that it's false, well, it's not false, it's true. Therefore, we return false. I apologize. This is a typo on the slide. It should return false here, right? Okay. Now, one thing that I want to impress on you, and this example does not do it, the next example will, is that compare and swap is actually exceedingly general. It is a very powerful instruction because when we actually read and do the load of the value from memory, and when we formulate what we want that value to be next, we can have arbitrary logic. Now, the longer that logic, maybe the higher the probability that somebody modifies that value in memory, and therefore our compare and swap isn't successful in updating the memory. But because it can be arbitrary logic, we can actually do quite a bit with compare and swap. But what we see here is similar to what we saw in test and set. That when compare and swap fails, so it does not successfully update the value in memory, we often need to recompute the next value that we want to set it to and do what's called a retry loop. We see that retry loop in a kind of very concrete way here, where we have essentially a loop that continues trying to update the value until it is successful. This is a retry loop that is just continuously trying to update the value, right? Because of this retry loop, we do not often have bounded weight, right? So because we cannot predict which of the threads that is trying to update the memory is going to be the one that is successful, we cannot guarantee that each of the individual threads is able to make that update on their own. Therefore, we cannot guarantee bounded weight. Okay, but here I want to blow your mind a little bit. So this is really, really cool, and this shows why compare and swap is really, really powerful. We can actually implement a stack data structure with compare and swap that will work without locks, even if we have many, many threads trying to do pushes and pops to that stack at the same time. And this should feel really strange to you, because when we talked earlier about race conditions, I actually used a stack as my first example of one of the problems that we have when we try to actually have a shared data structure accessed by multiple threads, right? So now I'm telling you that we do not need critical sections to be able to synchronize between threads on shared data structures. This is, to be clear, an advanced technique that you probably should never really use, but it does pay to know that it exists if you ever run into any problems where critical sections are not getting you enough speed, right? Critical sections serialize the execution of multiple threads, and what lock-free data structures do is avoid critical sections. They avoid that serialization. Instead, they just rely on the serialization only of the raw atomic instruction. So here is pseudocode for what you might think of as a push. If we have a list that's a stack, effectively, that we take in as an argument, this is what we're trying to add into the linked list. And we have some sort of a global head, which points to the head of the linked list. Okay, what we're going to do is we're going to try to modify that head to point to the temp. But we need to make sure that the temp also has its next value pointing to what the head points to, right? Because we essentially want to put temp as the new head, therefore replacing the old head, but we do need to track what was on the stack before. So what do? The first line within our do while loop is effectively trying to read a value from the head, do a load from the head value into a temp. Then what it's going to do is say, okay, we need to update the next value in the node that I want to add to point to what was previously on the head. So you can see, like I said, between when we're doing the load from memory and when we do the compare and swap, we can kind of do arbitrary computation. Here, we're updating our new node to point to what was formerly the actual head of the stack, right? And then what we're going to do is we're going to do the compare and swap, saying that I want the head value, which I believe right now is pointing to temp, right? It's pointing to what was previously the head. And I want to replace that temp as the head of the stack to actually instead point to my new node. So that has the effect of pushing my new node onto the head of the stack. And this is just going to say, all right, I want to continue trying to do this operation while the compare and swap is effectively not successful. If the compare and swap essentially says, yes, the head is actually set to the temp value, I'm going to replace that with to add. It has effectively updated the head of the stack. However, if head says, ooh, no, sorry, the head is not actually pointing to temp, that means some other thread has updated the stack in the meantime. Therefore, we need to retry our addition to the stack, given that head has been updated to point to someone else. This is immensely powerful, and lock-free data structures are a huge corpus of work that can often have better properties than those that use critical sections. But as you can tell, they get pretty complicated. Additionally, they are not a general solution. They do not work for any data structure. They only work for specific classes of data structures, usually those that essentially can be updated by updating a single word in memory, just like the head here for our stack, right? I'm going to ask you to do this now, but we are going to do this in class. I want you to think through what a lock-free operation for pop might look like. Okay, so this is my introduction to atomic instructions for providing critical sections, but also going a little bit beyond that. Atomic instructions are an amazing facility provided to us by the hardware, and they're a useful building block for implementing more complicated synchronization primitives. Next class, we'll talk a lot about some of those other primitives and how they're built from these raw atomic instructions. They get away from the requirements that we happened upon before of requiring O of n costs and software approaches. But generally, they give up bounded weight. This is a trade-off that people have just decided is worth the benefit of atomic instructions. However, some very clever people have found out ways to provide critical critical sections using atomic instructions. I'm not going to go over these in the class. If you're interested in this, then look up ticket locks. They're a really simple facility. They're not that complicated. They use fetch and add, which is again one of the simpler of these operations. And they're really, really cool. So you can look for implementations of that. Atomic instructions are pervasive. What I'm talking about in this class is not an esoteric issue. They are used in every system that you have used and that you probably ever will use. So they are pervasive. They're a very useful technique. I look forward to talking about them in class and diving into some specific implementation details with you. Thank you very much. Talk to you soon.